So let us come to the next class, that is the unsteady state heat transfer. So this is your 34th class on transport phenomena. Unsteady state heat transfer. Unsteady state heat transfer. This is the first part of the unsteady state heat transfer. After that, we will consider, in the next class, we will consider the second part of this unsteady state heat transfer, in which we will also discuss the heat flow or heat transfer study in the case of semi-infinite solid. And after that, in the next to next class, we will consider the heat transfer in the case of a system or in the case of a body which has certain finite internal resistance. So once these classes will be over, after that, in the next class, in the last class of this transport phenomena, I will go through some numerical problems for the entire class. One or two representative example for the Heisler chart, one or two representative example for the unsteady state heat conduction, and if possible for the Laplace equation as well. So in the next class, that will be the 37th class on our transport phenomena. In that class, we will go through some numerical problem in order to develop some flavor of the numerical problem that you should practice in this heat transfer portion. So, unsteady state heat transfer in the common general engineering applications, if you are going through the machinery which is used in the automobiles and the bikes, if you are going through the heat treatment process of any metallic plate, so all these are the general engineering applications, you will find that temperature in such type of system is a function of time, that is a function of time coordinates. Basically, the temperature of a body is a complex function of the spatial coordinates x, y, z and time. And so far as this unsteady state heat conduction is concerned, the value of this partial derivative, that is the partial derivative of temperature with respect to time, is not equal to 0 for unsteady state. This is the check for unsteady state heat transfer. On the contrary, in the case of steady state heat transfer, what we have studied, that the derivative upon dy small t, that should be equal to 0 for steady state heat transfer to happen. Such type of unsteady state heat conduction principle is of immense importance so far as the practical applications such as cooling of IC engine is concerned. Cooling of IC engine, that is the internal combustion engine is concerned, whether this is internal combustion engine is a spark ignition engine as in the case of petrol engine, or the compression ignition engine CI engine as in the case of the diesel engine cars and diesel engine trucks and other heavy vehicles. So the cooling of IC engine cylinder, this is an excellent example of the unsteady state heat transfer. Also, the quenching of metallic plate, is also an excellent example of the unsteady state heat transfer. That's why this portion of the heat transfer is regarded as one of the most important practical thing in the heat flow concept. So the first and foremost thing in the unsteady state heat transfer is the lumped heat capacity analysis according to your syllabus. So let us try to visualize what this lumped heat capacity transfer analysis is. Lumped heat capacity analysis. So first thing that we have to go through in this chapter is the lumped heat capacity analysis. Capacity analysis. Point number 1, it is defined as heat flow by conduction through the bodies having zero thermal resistance, So this lumped heat capacity analysis is defined as the heat flow by conduction through the bodies which have zero thermal resistance. So beginning with the simplest case, where the temperature throughout the solid can be considered uniform at all the times or at any instant of time This is the simplest case for this analysis of the unsteady state heat transfer problem. That is, temperature throughout the solid can be considered uniform at all the time. It means there is no conduction that is going on inside the body. So in that case, the entire heat transfer is taking place by the virtue of the convective mode of heat transfer. Once the heat energy reaches at the surface of the body and it starts to get convected through the fluid medium, that is the air. So this lumped heat capacity analysis is a type of analysis with such an assumption. So this is the assumption that is the lumped heat capacity analysis has. The next part of this class is to discuss about the validity of such an assumption. That what I have considered here, that temperature throughout the solid can be considered uniform at all the times. What does it mean? It means there is no internal temperature gradient. Because unless the temperature gradients are there, no conduction can take place. So, if the conduction is not able to take place, then the temperature of any point inside the body will not experience any temperature change. On the contrary, if the temperature gradients are there, then the heat will start to conduct from one place to other, and that gives rise to a difference in the temperature at all the points at all the time. So, let us try to investigate this assumption that what should be the condition in the system or body under which this lumped heat capacity analysis can be made applicable in order to solve the unsteady state heat transfer problem in practical situations. So, the temperature of the body is uniform at all the time. So, the aforesaid assumption of an uniform temperature can be a reality if, now I am giving you two examples for the time being now, that let us suppose we have two bodies, both have been heated at the same temperature. Let us suppose at up to the temperature of 200 degrees centigrade, this small body has been heated, this bigger body has been heated up to 200 degrees centigrade. For the same time, at the same temperature, it has been heated and left in the atmosphere, right? So my question is, which body will have the condition first that the temperature inside the body will be uniform? This one, because its volume is very, very less as compared to this one. So it is easier for this body to arrive at the uniform temperature throughout it. So the first conclusion which can be drawn can be, so this aforesaid assumption of an uniform temperature can be a reality if, number one, size of the body is very, very small. That means the characteristic dimension, which is often denoted as the Greek letter delta in the heat transfer case, is value of the delta is very, very small. Another is the value of the conductivity of the material, K is much greater than the convective heat transfer coefficient. When these two conditions persist, then the idealization of the fact or the conceptualization of the fact that an uniform temperature is there inside the entire volume of the present body can be made a reality. By combining these two conditions, the normal conditions under which a lumped heat capacity can be made applicable is the value of H delta upon K. This quantity is called a dimensionless number. This is a dimensionless parameter. It is called bio number. That should be much lesser than 0.1. Then the lumped heat capacity analysis may be used may be used to solve an unsteady state heat transfer problem. An unsteady state heat transfer problem. Heat transfer problem. So we talked about the lumped heat capacity analysis, its physical validation, and the conditions in which this can be used for solving a unsteady state heat transfer problem. Now come to the derivation part of this lumped heat capacity analysis. Now derivation of this lumped heat capacity analysis. That what are the governing equations for this lumped heat capacity analysis? Derivation. Since as the internal resistance is equal to 0, as the internal resistance is equal to 0 and heat transfer is unsteady in nature, it means body or system will be at different temperature. It means the body or system will be at different temperatures all the time. Is it not? Because the internal resistance is 0 and heat flow is taking place in unsteady state manner, that means if you measure the temperature of the surface of the body, so at every time it will give you some different value. So body or system will be at different temperature all the time. Also there is no heat flow. Inside the body. Hence we can write that is the d by dt of the internal energy of the body, d by dt, that is the time derivative of the internal energy E of the body for heat balance, that should be equal to how much? Heat transfer by convection. That should be equal to heat transfer by convection. Or you can write that is the d upon dt, that should be equal to h into a into t minus ta, where Ta is the ambient temperature, H is the convective heat transfer coefficient, T is the instantaneous temperature, and A is the area through which heat transfer is taking place. Heat transfer is taking place through the convection mode. Heat transfer is taking place. So So let us start from this equation itself now. So we can write internal energy of a body. So we can write d upon dt. Internal energy of the body is equal to mass into specific heat capacity at constant temperature into the temperature. So rho into V, that is the mass, into specific heat capacity at constant temperature Cp into T, and because assuming the cooling is taking place, let it be minus sign should be put up here. That should be equal to H into A into T minus TA, or we can write minus rho Cp V dt upon dt, that should be equal to H into A into T minus TA, or we can write dt upon dt, that should be equal to minus H into A divided by rho CpV into T minus TA, or dt upon dt plus HA upon rho CpV into T minus TA, that should be equal to 0. Let it be equation number 1. This equation number 1 is the differential equation for the lumped heat capacity analysis. This equation number 1, it is a differential equation for the present case of cooling, taking place in an idealized body, in unsteady state. So far as the different notations are concerned, as you have gone through earlier, that the rho and V are the density and volume of the material of the body, and Cp is the specific heat capacity at constant pressure, What should be our next task? You have obtained the differential equation for the lumped heat capacity analysis. So now it is our prime task to solve this differential equation, to put up the boundary condition there in order to evaluate the constant involved therein, and after that we have to make a conclusion regarding this lumped heat capacity analysis. So come to the solution of the equation number 1. Let us go through the solution of the equation number 1. So, solution of equation number 1. So the equation was dt upon dt plus HA upon rho CpV into T minus TA, that should be equal to 0. The separation of variable technique should be employed here. So dt upon T minus Ta, that should be equal to minus Ha divided by rho Cpv into dt. Integrate this equation, or we will get ln T minus Ta, that should be equal to minus Ha divided by rho Cpv into T plus a constant of integration I. So, initially the temperature, the instantaneous temperature of the body, that will be the initial temperature. Initially T is equal to Ti, that is initial temperature, and time T is equal to 0, that is the beginning. So putting this boundary condition or initial condition in the equation number 2, so we can write log E T minus Ta, that should be equal to this quantity will be 0, that's equal to I. Thus from equations 2 and 3, we can write ln T minus Ta, that should be equal to minus Ha divided by rho Cpv into T plus log E T minus Ta, sorry, T is equal to Ti, ln Ti minus Ta, sorry, Ti minus Ta, or we can write here log E T minus Ta divided by Ti minus Ta, that should be equal to minus Ha upon rho Cpv into T, or we can write T minus Ta divided by Ti minus Ta, that should be equal to exponential minus Ha divided by rho Cpv into T. So let us begin with this equation again. So let us begin with the equation that finally we have obtained. So we can write T is equal to Ta plus Ti minus Ta exponential minus Ha divided by rho Cpv into T, or we can write this equation further as rho into V, that is equal to mass, that is equal to Ta plus Ti minus Ta exponential minus Ha divided by rho into V, that is the m into Cp into T. Let it be question number 4. Another important thing is the term which is enclosed in the exponential parenthesis to express this term in terms of dimensionless number. Now, for a body of thickness 2 delta or for a solid cylinder of diameter 2 delta, the term in the exponential parenthesis, can be transformed as, see how it can be transformed, HA divided by rho CPV into T, that can be written as H delta by K into K by delta. So this stands for H completely. This stands for H into A delta by V into A delta by V. Let us suppose A by V, not introduce delta here, into A by V into T upon rho Cp into 1 upon lambda square. K H A T this one, or we can write it here H lambda by K into A delta by V, okay, into T by rho Cp into K divided by delta square. See, this is it intact or not? Delta square, that will be cancelled out. So H into A into T divided by rho Cp, this will get cancelled out, so V. Okay. Now it is all right. So this quantity H delta by K, this is called Biot number. A delta by V, this is another dimensionless number, that is called the dimensionless position. So this is called dimensionless position, abbreviated by letter G, and this quantity K by rho Cp, that is the alpha, into T by characteristic dimension square, that is called the Fourier number. So this can be written as Biot number into dimensionless position G into Fourier number. So basically this quantity is expressed as a product of 3 dimensionless number, because itself it is a dimensionless number. So it can be expressed as a product of 3 dimensionless numbers. 3 dimensionless numbers are there. So here you have to explain the meaning of G, that is the dimensionless position. G is called a dimensionless position. G is called here as dimensionless position. And it is a function of geometry of the body, as G is equal to 1 for an infinite plate, G is equal to 1 for an infinite plate, G is equal to 2 for an infinite cylinder, and G is equal to 3 for a sphere, It means as the geometry of the system or body changes, the value of the dimensionless position also changes as given through these values. So finally the solution equation can be given as, finally the solution equation can be given as, so T minus Ta divided by Ti minus Ta, that should be equal to exponential minus Biot number into dimensionless position into Fourier number. Also we can write T is equal to Ta plus Ti minus Ta exponential minus Ha divided by rho CpV into T. Let it be equation number 5. This equation is used for the cooling purpose. That means a body with an initial temperature Ti is subjected to cool in an unsteady state manner in the open atmosphere having the ambient air temperature at Ta. So once the value of Ti attains the value of Ta, that means after that there will not be any heat transfer, that T minus Ta is equal to 0, also a steady state condition starts to happen, or a very near to the steady state condition starts to happen. So this is for the cooling purpose. When the same equation is to be used for the heating purpose, then it needs to be transformed as Ta minus Ti, same expression, exponential minus Ha divided by rho Cpv into T. This equation can be used when the purpose of heating is there. What is the physical implication, what is the physical meaning of the equations number 5 and 6? Let us try to evaluate. What basically this equation number 5 and 6 tell us regarding its practical application. Now since both the equation number 5 and equation number 6 contain an exponential term, so if you draw the plot of temperature as a function of time in both the cases of heating as well as cooling, so let us suppose this is the Ti value and this is the Ta value, this is your Ta value, and the nature of this curve will be like this. That is the cooling, that is the equation number 5, that is the equation number 5. On the contrary, on the case of heating, the temperature of the ambient atmosphere is high, the initial temperature of the body is lesser. So in this case, the nature of the curve will be what is the physical meaning of these two curves, keeping equation number 5 and 6 in view. So this is your heating curve, this is your heating, that is the equation number 6. Because both these equation numbers 5 and 6 contain an exponential term, so that a sudden decrease in the temperature, that is the initial temperature of the body, is executed here, and once again the same body is subjected to an atmosphere having a temperature greater than the initial temperature of the body, what is happening? This body will start itself to attain the temperature of the ambient air, and the cooling heating starts to happen. In both the cases, we can see the steeper nature of the curve. That the steeper nature of the curve can be explained or can be attributed to the exponential terms involved in the equation number 5 and 6. This is the first conclusion. This is the first practical thing. Another thing is, in both the cases of cooling and heating, you can easily visualize that the curve become asymptotic with respect to the temperature axis after some time. The practical meaning of such a thing is that in the case of the unsteady state heat transfer, this d by T upon d by T will never equal to 0, and that's why the curve doesn't cut this temperature axis, this time axis, because once it will cut, it means its value will equal to 0. But in both the cases, that is in the case of cooling as well as in the heating, in both the cases the heat flow is taking place in an unsteady state manner. However, the cooling body or heating body, in both the cases, the body will arrive at a condition which is very, very near to the steady state condition in a very quick time. So, practically we can say we can say that even though delta T upon delta T is not equal to 0, but the body during its cooling or heating arrives at a situation very similar to a steady state condition, in a quick time. This is attributed to the exponential term involved in equation number 5 or 6. Okay. This is the first conclusion which can be drawn, and the second conclusion which can be drawn is number 2. Better to say right here separately. And the second conclusion which can be drawn, since the curve becomes asymptotic with respect to the time axis, since the curve become asymptotic with respect to time axis, it means an infinite time will be required by the body to attain a fully steady state condition. In the next class, we will see that how such concept of unsteady state heat transfer and the lumped heat capacity analysis can be utilized to determine the instantaneous flux in the body, as well as to arrive how this concept can be utilized to determine the quantity of heat lost by the body in a particular length of time. Apart from that, we will also study in the next class that how the heat transfer takes place in the case of a semi-infinite solid, such as in the case of ladle cooling and ladle heating, as well as other semi-infinite heat flow situations. Thank you.